Hi, my name is Sandeep Kumar. Today I'll be presenting our work SecureLease, that is about maintaining execution control on the application that is running on remote machines. Here is an outline of the talk. I'll start with the problem statement, followed by the prior work and the motivation behind the work. Then I will discuss the design of SecureLease. This will be followed by some results and finally the conclusion. Let us start with the problem statement. Modern application contains different functionalities. Some of them can be access controlled. That is, they require an additional payment before those features can be accessed. Furthermore, they can also contain different plugins that are developed by independent third-party vendors. These plugins may also require additional payments before they can be used. To control access to those plugins and those features, generally a license manager is employed. The plugins can use their own license manager since they don't trust each other and they certainly do not trust the main application. The working of a typical license manager is something like this. If the user has a valid license file, after the init phase, it passes the license file to to the application that validates it using an authentication module. If the license is valid, the control flow is allowed to proceed to the protected region. That is the feature that was access control. This is a typical flow of the license manager. If the user does not have a valid license file, then the authentication module will abort the application because the validation of the license file will fail. However, there is a certain class of attacks called control flow blending attacks that basically hijacks the control flow. And even if the license is not valid, the execution can go to the protected region. This is based on a general idea that the final decision to whether to continue the execution or abort is based on a conditional branch statement. The attack can force the branch to be always taken, irrespective of the condition. We were able to use this attack to break the security of the MySQL. The details are in the paper. Here is one typical example of a control flow bending attacks. Suppose developer releases software with it in a trial-based mode. That is, it allows 10 trial executions before the user has to buy. Once the user has exhausted its 10 executions, it will ask developer for more executions. Developer simply will ask the user to buy it. In that case, the user can mount a CFB attack, that is a control flow bending attacks, and can keep using the software without paying the developer. This may result into a significant loss of revenue for the developer. There are many instances of attacks where license managers have been bypassed to steal sensitive information from the application. Also, bugs in plugins have been exploited to steal information from the application. Next, we will discuss the prior work and the motivation behind the work. In our prior work, we leverage Intel SGX software guard extension that allows for a secure execution of an application that is guaranteed by the hardware. Any tampering with the application's code, data, or its execution flow will be detected by the hardware and the execution will halt. We also use a feature called remote attestation. This is part of SGX, where a remotely executing application on SGX can be validated before sending it sensitive data such as encryption keys. Needless to say, since the hardware guarantees the security of the execution, there cannot be any CFB attacks on the application. Here is an overview of our prior work. We notice that an application contains many different functions. Not all of them will require security. We divide an application into secure and unsecure region. From the secure region, we remove certain functions and hence handicapping the binary. That is, if you run this binary, it will result into a crash since certain functions are not present in the application. We then send this application to the user. The user has to provide a valid key or license before those functions will be sent remotely to the user via an Intel SGX mechanism called PCL, or protected code loader. In this way, you can actually patch a running binary using encrypted code, and that is only done when the user actually has a valid license file. If the user tries to mount a CFB attack on the application will just crash since the functions are missing. Needless to say, the secure region, the protected region, and the license check manager will be running in SGX so that they are free from the tamper. There is an execution flow when the application is running within SGX. The developer sends a handicapped binary to the user. The user needs to contact the software every time it needs to execute the application, since the binary is handicapped. Every time the user accesses the controlled region or the secure region, it sends its key to the developer. The developer checks whether the key is still valid or not, and based on that, it responds. Now this solution works. It actually is secure, and the developer has a full control over the execution. So the user cannot run the application if the developer says no, or the developer is not available. Now, but this is too slow, since the remote attestation step in the SGX can take around 1 to 2 seconds, and this might not be suitable for certain use cases. Hence, in this work, we aim to improve the speed of the license checks, make it scalable, and also provides a way to execute it when the network is unstable. Now we will discuss the design of SecureLease. So we keep the basic design same. Then application executing here also the application is executing within SGX, and we have a license manager called SL manager that is running within SGX, so that we know that it has not been tampered with. Now instead of contacting the remote server every time, we maintain a local cache of the leases. So a single lease is basically a single unit of token that allows one execution. So corresponding to a single key, there can be many leases. Suppose a key allows for 10,000 execution, then corresponding to that key, there can be 10,000 leases. So we maintain a local cache of these leases. This cache is populated by the secure remote server during the init phase, or once when the application is executed for the first time. This solves many challenges that like contacting the remote server every time while the application is executing, and the local cache can actually serve even if the remote server is not reachable, but it has populated leases in the local cache. But at the same time, there are certain challenges associated with this design. Like we have to maintain the security of the local cache. Then we have to decide when to renew and approximately how many leases should be given to the local cache. And what if happens if the local machine crashes, right? Because the cache is on the local machine, and if the machine goes down suddenly without graceful shutdown, what to do with the leases that was stored on the machine? We'll start with the organization of the local cache. The organization is inspired from a page table, from the design of the page table. We organize all the leases in a tree-like format. A single key is a 32-bit integer. We use the bits in the key to actually to index into the different level of the tree. This allows for an efficient lookup of a lease file associated with the key. This also allows for an efficient memory uses of the users, since if a portion of the tree is not used, it can be offered to the secondary storage. Furthermore, the leases that are accessed together can be grouped into under a single parent which will actually improve the performance of lookup. So here's the distribution of the leases. So the design allows for concurrent access for a single key. So the remote server actually sees many factors and then decides how many leases it has to allocate. By default, it will allocate an even numbers to all the concurrent accesses. But suppose if it sees that one of the node or the requesting node is unstable, that it can go away anytime, it can crash or something like that, then it will actually reduce its quota, because if the if the node crashes, all the leases that is stored into it will be lost. This is required to prevent a rollback attack. Details are in the paper. Furthermore, if it sees that a node has an unreliable network, then it will actually increase its quota. This is to ensure that it can actually service many local requests in case the network goes away. Now we will discuss some results. To measure the performance of SecureLease, we use a suite of workloads that is specially designed for SGX. The suite contains workloads from different domains, such as tree-based algorithms, hash, encryption, etc. We configure our remote server to populate 25% of leases every time there is a request from a local cache to populate the lease, to populate leases. As you can see, the local validation takes less than 1% of the total execution time. The majority overhead comes from the remote population of the keys, of the leases. Now this can be reduced by tweaking the setting of the remote server. It can allocate more than 25%. It can go to 50%, 75%, 80%. That depends on the scenario in which SecureLease is employed. To conclude, we show that there is a requirement for a secure, fast, and scalable license manager. We show that SGX can be used to prevent such kind of attacks and to develop a secure license manager, but the cost of certain SGX operations is quite high. We propose a design that mitigates these costly operations and allows for a very fast license manager. Furthermore, we also developed novel techniques that allows for distribution of these leases and a fast lookup of the cache on local machines, on local hosts. Now, the development was done on an SGX version 1, where the total amount of secure memory was limited to 128 MB. However, Intel has announced a new generation of SGX, where the total amount of secure memory can go to up to in terabytes. But at the same time, they have reduced, in order to support this large amount of memory, they have reduced the security guarantees. It will be interesting to see how SecureLease can be adapted to this new generation of SGX. Thank you. If you have any questions, please do reach out to us.